Yo, got no joiners today, but we are doing the last Zoom session on 110 acoustics. Today is Tuesday, November, I don't know, 27th, something like that. Yes, November 27th, our last Zoom session. Next week, I'd like to hold a review session at the same time, covering lots of stuff in an acoustics course from A to Z, from the beginning to the end. And your final exam in this course will be mostly on the second half. I'd say 75% of the content of your final exam here in this course will be on the stuff covered from the midterm until now. But I reserve the right to put about 25% of the questions, will entail or involve stuff from the first half of the course. So it still behooves of you to know what frequency is 1 over the period, period is 1 over the frequency, wavelength is speed of sound over the frequency, frequency is speed of sound over wavelength, and the dBSPL equals 20 times the log of x over 0.0002 dynes per centimeter squared. There you go, there's a mouthful. Stuff and things. What we want to do today is finish Unit 7, our last unit, the one we began last week on non-electronic acoustic modifications. Last week we got down to the bottom of page 1 in your notes. We covered the 3 types of non-electronic acoustic modifications, but we'll finish that section today. The main 3 are venting, and that's the big one. That's the one that's still used commonly today in all digital hearing aids. The second one is filtering, and the third one is horns. Now, venting reduces the occlusion effect, and it's especially useful for people who have good low frequency hearing. And we showed you vents on hearing aids last week, but let's just take you to these things here. Let's share the stuff here, and we'll go to sharing the files, and I will now pull up our notes, and there we are. Okay, I'll make it a little bit bigger, and now we said it's a lost art, but this whole first paragraph deals with remembering the ear canal as a quarter wave resonator. Remembering the ear canal as a quarter wave resonator. Very important to retain that particular concept, even regarding anatomy class 120, because this is the physiology of the outer ear. Okay, remembering that the outer ear canal is a quarter wave resonator. It's going to resonate with sound waves 4 times its length. Working that all out with the formula frequency equals speed of sound over wavelength. If the ear canal is 2.5 centimeters long, it's going to resonate best with sound waves 10 centimeters long. 10 centimeters is 0.1 meter, and 340 meters per second, the speed of sound divided by 0.1 will give you 3,400 hertz. But the ear canal is not, and here you go. But the ear canal is made of flesh and bone, and therefore the resonant frequency is spread out a bit. So really be able to draw this outer ear canal resonance and give its value in dB. That is about 20 to 25 dB. Okay, so that's very important because that particular stuff is lost. And I'm going to share screen here. That stuff is lost, well, somewhere. There you go. Nope. Here. That stuff is lost when you plug up an ear with a hearing aid. So there's an open ear canal right there, and it's the sound coming in. You've got the outer ear canal resonance. To us, we hear it as normal. When you plug up an ear, of course, you lose that resonance. Okay, you may think you're getting what you're seeing here on this first box, but actually you're getting what's shown on the second box. Okay, and that's why that first half of page 1, that's what it's all about. Then last week we worked our way down through types of ear molds and materials, and I said that the most important things to remember about that particular topic is this. We'll make this, is 2 ear molds here. On the left, the full shell, and on the right, I should say in the middle, the skeleton. Don't worry about the other ones, okay? The full shell ear mold has number 13 tubing, which is 2 millimeters in diameter, 2 millimeters in diameter. And the skeleton ear mold has the same number 13 tubing, 2 millimeters in diameter, but both of those are meant to be used on hearing aids that are high power. Usually the hearing aid will look a lot like what I'll show you here, okay? A high power one, so let's just stop sharing and I'll show you. A high power hearing aid with a full shell ear mold, number 13 tubing, and if I take it off, it's 2 millimeters in diameter, the hole, okay, 2 millimeters in diameter, and this particular mold is made out of silicone. Look, I can bend it. It's rubber. So when you see a full shell silicone ear mold, please think high power BTE. You're plugging up the entire ear canal and you want that silicone to stick to the skin of the outer of the ear canal so you're not letting anything out. Notice there's no vent here. Okay? It's not much happening there at all. There's no vent. Solid. Okay? So this guy's got one heck of a hearing loss. Now, a lesser degree of hearing loss would be shown with a mold looking more like this, a lucite skeleton. And notice I can't bend it. It's hard. It's made of plexiglass. And it's got a vent in it. So if I hold this nice and close, you can see two pathways, two of them. One for the number 13 tubing and the other one as a vent. Okay? So this guy's got less of a hearing loss, and he may experience the occlusion effect. And it's especially, venting is especially important for people who have good low frequency hearing in the lows, okay? Because the occlusion effect is a low frequency phenomenon. Now, speaking of the occlusion effect, make sure that you can outline the lay definition and the professional definition of the occlusion effect. Here's the lay definition, the common person's definition. My voice got louder when I plugged my ear. Okay? The professional definition has 5 parts. Write them down if you don't have them. Low frequency, bone-conducted sounds resonate the mass of your skull, which in turn vibrates the cartilaginous portion of your ear canal. Plugging your ear prevents that from escaping. So if you're asked, be able to rattle that off. Okay? 5 pieces to it. It's why when you plug your ear and you say the letter S, it's not much louder. But if you say the letter M, you really hear a difference. You see, is lower frequency than S. And that's why the occlusion effect is a low frequency phenomenon. So people who have good low frequency hearing will experience the occlusion effect when plugging up the ear with a hearing aid. They will need a bigger vent. People with a flatter hearing loss will need a smaller vent. They experience less of the occlusion effect. And you will notice this on your fitting software. When you're fitting hearing aids, you're going to be asked, you're going to be asked to say, what kind of dome do you want to use in your hearing aid? And what I mean by dome, of course, and some of you may know already, but what kind of dome will you need? Pull out my little bag of tricks here. See if I can find a dome. There you go. What kind of dome do you want? Do you want a dome with a lot of holes in it? See if I can show you there. If it sounds, looks, there you go. Look at the holes. 4 of them. That's a big vent. Okay? Do you want a vent with lots of holes in it? Or do you want a vent with fewer holes in it? And it's your software may even recommend. You've entered the hearing loss into NOAA, and it looks like this. We recommend a more closed vent. Okay, it may even do that, or it may say we recommend a more open vent. So your software will guide you because you've entered the hearing loss into NOAA, and the hearing aid software picks up the audiogram from NOAA, and part of the acoustic parameters it's going to ask you about is the venting. So these are things to keep in mind, and that's why we're trying to go over non-electronic acoustic modifications. And if you're wondering what NOAA is, that's the fitting software ARC. Okay, the Ark of the Cut. No, it's the Ark that Noah had through the flood. It took all the animals on it. NOAA is a program that takes all the hearing aid manufacturers' fitting software, and it plays with all of them. You enter the client's address, phone number, name, and audiogram into NOAA, and then you pick a hearing aid company. Is it going to be Oticon, Bernafon, Unitron? Notice how they all end in on. Widex, Starkey, what are you fitting? And once you've chosen your software, then your software guides you through the fitting of the hearing aid. And one of the things it's going to ask you is about venting. So these are things to keep in mind. All right, share screen, back to the notes. Look at the notes here. General frequencies of acoustics, ear mold acoustics. You've got venting, damping, and horns. Okay, so venting is the big ones. Horns and filters were relied upon heavily in yesterday's analog hearing aids, not so much in today's digital hearing aids. There's a tension between vents, horns, and feedback. Horns increase the highs, and we'll look at them in a bit here. And when you've got lots of high frequencies coming into the ear canal, highs are short little waves. They bounce, and they're going to leak out of your vent, and they're going to get picked up by the mic of your hearing aid again. They'll be amplified. They'll whistle down through the tubing and bounce off the eardrum and leak out of the vent and get picked up by the mic and get amplified, and the circle continues. Remember we said last week, it's like you talking into a mic and you go too close to the speaker, and now not just your voice is going into the mic, but also sound from the speakers going into the mic. So you got to back away from the speaker. Otherwise, you're going to get feedback. Feedback is a real danger. It makes the hearing aid unwearable. It's the whistle. You don't want it. Okay, venting. Remember Select Vent, SAV, okay? That allows you to choose the size of the vent. So let's look at a picture of SAV. Select Vent. That would be shown in this particular slide here. You've got a hole dug into the mold, the bottom tunnel that you can see on the left, and the black plug there is the Select Vent. And they are in different millimeter widths. So you can choose based on what your client says or what your software says you want to do, okay? This is going to be in a mold. Excuse me, this is not pertaining much to a dome. A dome on the end of today's hearing aids, domes are stock. In other words, they come out of a box. You can choose a dome with no holes in it, a dome with a little bit of holes in it, a dome with more holes in it, okay? That's how you're choosing the vent size in today's hearing aids. And today's hearing aids are often called RIC, receiver in canal. Okay, the receiver isn't up here. The receiver is actually in the end piece. So if I show you, this one here is a thin tube BTE. The internal diameter here isn't 2 millimeters. The internal diameter here is about 0.8 or 0.9 millimeters. This is a thin tube one actually. The receiver is up in here, and the mic is here where the hole is. Okay, you see that hole there? That's where the mic is. The receiver is just inside the top of the hearing aid, and the receiver is the speaker. And the speaker, that's why they call it, I know it's weird, receiver is the speaker. Remember, hearing aids have two transducers, a mic and a speaker. The mic changes sound into electricity, the hearing aid amplifies the electricity, and then the speaker changes it into sound again. So a speaker is just a backward mic. A mic is a backward speaker. A frown is an upside down smile. A smile is an upside down frown. Okay? So, and in hearing aids, the speaker is called a receiver. It's because it receives the current. You and I would call it a speaker. Anyway, thin tube, and then sending it out into the dome. And remember, this little thing here mainly sits inside my concha bowl to help hold the hearing aid dome in place in the canal. This hearing aid is called a receiver in canal. Looks the very same, except the receiver, the speaker, is this. And then you take a dome and you put that on top. So if I do that, there you go. So it looks almost identical to the other one. If I hold up the other one, look at that. A man on a flying horse wouldn't even recognize the difference, okay? But this one here is usually more expensive because the receiver is now closer to your ear canal. It's in your ear canal, the speaker. You can actually see the box, okay? Whereas here, it's just a tube. Here, the receiver's actually in that steel square, okay? Just so you know, two types of hearing aids extremely popular today. They're both BTEs, behind the ear. One's a thin tube, one's receiver in canal. R-I-C, RIC. Sometimes they're called RITE, R-I-T-E, receiver in the ear. RITE or RIC, thin tube BTE, RIC, okay? Hold these, and the thing about a RIC hearing aid is that the tubing here has a wire going through it because it has to connect to the speaker. Whereas the thin tube, sound goes through the tube. The RIC hearing aid here, this one has a wire going through the tube, so no sound is going through the tube. The sound is coming out of here. Whereas in the thin tube, the sound is coming out of here, and it's being delivered through the tube. Much like the sound is being produced here, and it's going through the tube. Okay, so the thin tube and the regular tube BTE, okay, they're close cousins. This one's just for milder hearing loss. This one's for more like a severe loss, and this one here would be like for a profound loss, okay? And so for mild to moderate hearing losses, which are the most common hearing losses in the world, RICs or thin tubes. So most people today have mild to moderate sensory neural loss because that's what typical average presbycusis is. Mild in the low frequencies, moderate in the high frequencies. Common as the day is long. So fewer people are wearing hearing aids like this. And these are like the beige bananas, aren't they, that fit behind the ear? Fewer people have severe hearing loss. Most people have mild to moderate. Okay, stop sharing or start sharing again. And so there you go. Let's look at our notes now and work our way down. Vent sizing. Vent sizing is about 1 millimeter to about 4 millimeters. 1 to about 4. A pressure vent is a 1 millimeter vent. Very narrow. It's a very tiny hole. Hardly does anything to the sound. Not much at all. It's mainly meant to equalize the air pressure from outside the ear versus inside the ear canal, so that when you take the hearing aid out, you're not pulling out your eardrum, okay? It's just but when you start getting to 2 millimeter and 3 millimeter, well, now you're getting effects of the venting. So there's what venting does. As you see the size of the vent, it starts to let out more and more of the lows, thus reducing the occlusion effect. Look at what it says on the bottom there. Influence of vent diameter on the occlusion effect. Here, again, same thing. This one's showing it in terms of output in dBSPL. This one's showing the same effect in terms of gain in dB. Same thing though. The bigger the vent, the more the lows are let out. It's done to reduce the occlusion effect. And now we're going to just have one little piece here. It talks about parallel versus diagonal vents. All that means is in the old days when people made diagonal vents, okay, they don't work as good as parallel vents on the top. Okay, but again, this particular PowerPoint slide, it only refers to hearing aids that look like these, because only these have ear molds. Okay, these are simply stock domes, and you're picking the size according to the person's ear canal, out of a box, stock. Okay, domes versus molds. Okay, share screen and look at our notes and our PowerPoint. So let's look at PowerPoint here and go down to here. Now you're going to turn your notes to the top of page 2, because the top of page 2 is now dealing with the second modification. And the second modification is due to what's necessary when you're looking at what's called here the frequency response of the hearing aid. The frequency response of the hearing aid. Look at this graph here. What does it say along the horizontal axis? Frequency. The vertical axis, dB/SPL output. Now remember from acoustics course earlier on, input plus gain equals output. Input is the sound coming into the microphone of the hearing aid. Gain is what the hearing aid is adding. Output is the sum total. Input is always dB/SPL. Gain is always simply dB, because it's a relative value, and output is dB/SPL again. Okay, so input and outputs are always dB/SPL. Gain is always dB. And remember from earlier in acoustics course, okay, dB/SPL is an absolute value. It's referenced to 0. It's referenced to the ground, whereas gain is not. I can add 50 dB to a 10 dB/SPL input. I can add 50 dB to a 20 dB/SPL input. I can add 50 dB to a 30 dB/SPL input. And as long as you're adding a dB to an absolute, you can add them like 1 plus 2. So 10 dB/SPL input plus 20 dB of gain is 30 dB/SPL output. 20 dB/SPL input plus 20 dB of gain is 40 dB/SPL output. As long as you're adding an input in SPL and a relative together, you can add like 1 plus 2 is 3. Remembering that from Unit 2 in acoustics. Okay, look at our notes now, and we'll talk about filters. So let's move on down to the top of page 2. The top of page 2 is dealing with this particular PowerPoint slide. This is a frequency response of some imaginary hearing aid in dB/SPL output. So you're looking at the peak output is around 120 at 1,000 hertz. And then you've got 5 other peaks. And these peaks are due to resonances of tubing and pieces inside the hearing aid. Okay, they come from the resonances of the internal guts of the hearing aid. No, don't think you have to memorize these, because I don't know what they are either, so leave them alone. Just realize that peaks in the frequency response of a hearing aid come from the internal resonances of the pieces and parts inside. Now, these peaks don't always sound good to people, and they also cause feedback. Feedback occurs due to high frequency peaks in the frequency response of a hearing aid. Filters are like tiny little screens that are meant to provide resistance. Now, this harkens back to earlier stuff in acoustics as well. What is resistance? Remember, we covered in acoustics the topic of impedance. Impedance is comprised of opposition due to mass, opposition due to stiffness, and resistance. Those 3 things put together gave you an overall thing called impedance. And impedance is the flip side of resonance. So what isn't impeded goes through. And what isn't allowed to go through is impeded. Okay? So objects that transmit sound all have their own unique impedance. They have favorite vibrating frequencies, like a wine glass at Christmas. Okay, so the resonance is created from the impedance. The impedance blocks certain sounds and therefore allows others to get through. Those resonate. So think of impedance as upside down frown. Okay, resonance is the smile turned around. It's all it is. They're flip side. Just like a mic is a backward speaker and a speaker is a backward mic. Think impedance is the opposite of resistance. Resonance, and resonance is the opposite of impedance. So what is impedance created out of? Opposition due to mass. So mass doesn't let highs get through, and stiffness doesn't let lows get through. So obviously those are very frequency specific. Resistance in any object, resistance is simple friction. And in any object, its resistance is equal for all frequencies. Okay? So you've got the three parts added together create overall impedance. And whatever is not impeded, of course, resonates. So let's look at filters now. Filters in a hearing aid. Share screen. Filters in a hearing aid are tiny screens, and they provide resistance, not opposition due to mass, not opposition due to stiffness. So they are going to provide equal resistance for all frequencies. So in a frequency response that has a bunch of bumps in it, all of those bumps are going to be reduced because resistance applies to all frequencies. Resistance in an object applies to all frequencies going through it. So what do filters do? They reduce the peaks in a frequency response wherever the peaks may be. And since most of the peaks in a frequency response, the biggest ones tend to be in the mid to highs, that's where the effect of filters will be seen. So filters make the sound quality better. They make the sound quality better for the listener, and they also reduced feedback, okay? Because they dampen the peaks in a frequency response. And what causes feedback? Mainly high frequency peaks in the frequency response. Remember, highs leak out, highs bounce. So those peaks that you saw, those are going to be the ones that escape and get picked up out of the vent and get picked up by the mic. So in the old days, with analog hearing aids, you provided a filter to get rid of those peaks. Now, you might say, what the heck where are they? Well, here's where they are. Look at that little red thing in the hook. That's a filter. Okay, that little dot right behind my finger. That was a tiny little screen. See if I can find you another one here. See that little gray thing at the end of the ear hook? Okay, this is the ear hook. Okay, that little gray thing, that's a filter. A little tiny screen. Okay. Anyway, so those are filters. And filters is the second acoustic modification. Guess what? They're not relied on much today anymore. We don't need them anymore. You know why? Because we have digital hearing aids. And digital hearing aids, like these RICs and thin tubes, digital hearing aids have automatic feedback reduction. You know what they do? They actually pick up the feedback, and then the hearing aid learns the frequency of the feedback, and the hearing aid then produces, get this, a frequency in opposite phase to the feedback, and cancels it out. Automatic feedback reduction. How is it achieved? By digital phase cancellation in hearing aids. So we don't need filters anymore. See, the reason filters are not always so great is because they get plugged up with perspiration. They could easily get plugged up with perspiration. And then the hearing aid's dead. It's not working at all. And the guy's changing the battery, and it's still not working. Brings it over to the clinician, and then you'd have to twist off the hook, okay, and dig in your drawer and find a new one, and twist it back on and turn the hearing aid on. And by the way, feedback is your friend when you're checking out how a hearing aid is working. It really is. I wonder if I can even show you this. I might even, let's see if I've got the kind of battery that you would need, that I could show you feedback. I could make the hearing aid whistle on purpose. I wonder if I can. This is one thing you should always know about feedback. Let's see if I'm not 100% sure if this will work here, but I'm going to stick a battery into this hearing aid. Here's the battery door. I'm going to close it. You hear that whistle? Okay, that's feedback. It's sound leaking out of the ear mold and getting picked up by the mic of the hearing aid. And the mic of the hearing aid is that little dot right there underneath the ear hook. See that little dot? If I close the ear hook, now the dot is underneath the ear hook, but the ear hook has a hole. It allows sound to get in. With the hearing aid, especially when I put my hands around it. Feedback is your friend when you're troubleshooting a hearing aid. If you can make the hearing aid feedback when you put it on and cup your hands around it, that means the hearing aid's working. Okay? If you can't make the hearing aid produce any feedback when you put a battery in the hearing aid and you put your hands around the hearing aid and it's not whistling, something's wrong. But the feedback is your enemy when the person's wearing the hearing aid. Well, then you don't want the feedback. But as a clinician, you want to be able to create feedback, and especially when you hold the hearing aid and cup it in your hands, that's going to make it feedback more because the sound's going to bounce off of your hands and get picked up by the mic. So you're really aggravating the feedback when you start closing, when the person's wearing a hearing aid and you put your hand around it, that will make the hearing aid whistle. Okay, but today's digital hearing aids have automatic feedback reduction. We don't rely on the use of filters. So if we share screen once again, and we start looking at our notes on filters here, and you can just read with me right through. Very simple. We've covered it all. Not much used anymore. Their purpose was to smooth the frequency response peaks and reduce feedback. Reduce especially the mid to high frequency peaks because these are the ones prone to cause feedback. They also reduce the harshness and sharpness of sound quality. Filters reduce feedback caused by sound leaking out of the receiver and being picked up by the mic. It's especially caused by high frequency peaks. Reduction of feedback allows the client to turn up the volume control more without getting the feedback, because the old complaint was, I turn the hearing aid up to here and it whistles. I turn it down to stop the whistling and I can't hear. Okay? You're caught between a rock and a hard place. Filters cause acoustic resistance, which is independent of frequency. Filters were thus measured in ohms. The more ohms, the more resistance. So the more ohms, okay, the tighter the screen. This screen dampened the peaks more than this one did because the screen was tighter together. The largest peak in number 13 BTEs, the largest peak in these hearing aids with number 13 tubing, the largest peak was usually at 1,000 hertz. So if I go to 1,000 hertz here, okay, the largest peak was usually at around 1,000 hertz, and still is. That's why when you look at the frequency response of a hearing aid, and you'll learn more about this next year as you get into the program more, you'll do a test called ANSI testing, ANSI, American National Standards Institute, which applies to everything, light bulbs, toasters, anything that works with electricity. At any rate, you're going to, hearing aids have electroacoustic analysis testing done on them. You'll be running a test to see what the frequency response looks like. Is it good or is it not? Does it match the hearing aid specs or does it not? And then you'll do a listening check and you're going to try and get feedback. And you're going to listen to the hearing aid and listen to what it sounds like. So these are all things that play together. Okay, so the more ohms, the tighter your screen was together. Over to your notes. They used to use lamb's wool as an early type of filter. Then they got to screens. Anyway, you don't need to memorize this. This is not important anymore because it's no longer really used. Okay? Locations of filters at the small end of the BTE ear hook. In ITEs, it was often just inside the receiver. ITE hearing aids, just inside the receiver. In the ear hearing aid, okay, just behind the speaker. Okay, stop sharing. Okay, problems with filters, they can get plugged up with wax due to perspiration. You can't clean a filter, you'd have to replace the entire ear hook. Note on PowerPoint slides where filters were seen in BTEs and ITEs. Look at this, you're getting lots of peaks being reduced. The more the ohms of the filter, the tighter the screen, the more the reduction of the peaks. And then this weird slide talking about where the filters were placed, whether over here, or over here, or over here, or over at the end. Don't worry about this slide. Nobody uses filters like this anymore. This is yesterday's stuff, okay? The last acoustic modification is horns. Horns. Now, the simplest thing to know about horns is this little demonstration. If I take a piece of paper and I roll it up like a horn, well, it's wider at one end and narrower at the other end. If I talk into the horn, you can hear the high frequencies of my speech. Okay? Horns increase highs. If I talk into the wide end of the horn, the opposite happens. Now my speech is muffled. Now my high frequencies are reduced. So horns were a very cheap way of increasing the treble frequencies of a hearing aid. And most people have trouble hearing treble, right? Most hearing loss is worse in the high frequencies than in the low frequencies. So horns provided a, look at this, on the left, increase the highs. If you talk backward into a horn, into the wide end, you reduce the highs. So, the bigger the horn, look what they did. The tubing, here's number 13 tubing, and it's 2 millimeters in diameter. And if all of a sudden in the mold itself it got wider, that's called a horn. The most popular horn was a 3 millimeter horn. They called it a Libby horn, a 3 millimeter Libby, L-I-B-B-Y. That was the most common horn. Now look, as you keep moving toward the bottom, this horn gets smaller. This horn doesn't have a horn at all. Now you're getting a reverse horn, and now you're getting even more of a reverse horn. So you can see as you go from the top toward the bottom, look at the effect it has. The thick black line would be no horn used. And if you start to flare it out, you get more highs and more highs. If you make the horns narrower than 2 millimeters, you're dampening, you're getting rid of the highs. Okay, so these bottom two would be a reverse horn. The middle one is no horn, and the top two are smaller and bigger horns. So basically, looking at that situation here, let's go to our notes. Horns. Not much used anymore. The flaring does increase the high frequency gain. Horns reduce the impedance for high frequencies. Experiment with a rolled up paper for yourselves. Horns were located at the end of BTE ear mold tubing. Where were they located? At the end of BTE ear mold tubing. At the end of the tubing. So if I show you here, the horn would be inside of this little piece here. The end would not be 2 millimeters in diameter, like this hole. The end would be bigger. If I can show you one little, here's just a, I don't have a mold that has it, but here is a foam earplug. This is number 13 tubing, but notice how it gets wider there? That's 3 millimeters. So the diameter of that is 3 millimeters. The diameter of this tubing and the hole at the end of this mold, the top one, is 2 millimeters. Okay, so I don't know which way I'm holding closer here, but anyway, this is an example of a horn. Pretend that this is an ear mold. The horn was flared into the ear mold. And in ITEs, the same thing. Okay, you'd see a larger hole at the top. Remember, the bottom one's a vent. You just see it would just flare out. So that was the purpose of horns, but they're not used very much anymore. Okay, because today we've got digital hearing aids. And digital hearing aids, you can sculpt and shape the frequency response much more. So we don't have to rely so much on the physical flaring of the tubing to increase the highs of a hearing aid. So filters and horns are kind of like yesterday's news. We don't rely on them much. When did analog, they were used in non-digital hearing aids, and non-digital hearing aids were called analog. Analog hearing aids were the thing all the way until 1996. All hearing aids were analog. Okay, they weren't digital. In 1997, digital hearing aids emerged. And that's when analog hearing aid technology became yesterday's news. So for the past 20, 25 years, hearing aids have been digital. Okay? They're programmed on a computer. They're programmed with software. They're programmed wirelessly. You no longer need to physically change what the hearing aid is doing with a tiny screwdriver that look like this. Just like eyeglass screwdrivers. In old analog hearing aids, if I open up the back of the hearing aid, you'll see tiny little screws. And those tiny little screws are what the clinician used to adjust physically. And the little screws would be increasing the highs, increasing the lows, stuff like that, increasing the maximum output that the hearing aid could deliver. And the clinician would physically adjust that. Much like turning a living room light switch. Like a dimmer switch. Okay, the more you turn the screw, the more the effect was. That's called potentiometer in electronics. That's called a potentiometer. We don't do that anymore. Hearing aids are run on digits, zeros and ones, all algorithms. So they may look somewhat similar, but the hearing aids are programmed digitally today. So let's take this particular unit home so we can put it to bed. Okay, horns are done. So now we've talked horns. Move on down. Tubing in BTEs. For regular BTEs, like number 13 tubing, it is 2 millimeters in diameter. More width gives more highs, like horns. More length tends to give more lows. Don't worry about that. Client with high power BTEs, beware of old, narrow tubing. It cuts off the highs. What do I mean by that? If this tubing here is a couple of years old, it's no longer nice and flexible. It becomes quite stiff and it kind of shrinks in its width. And that's when you need to change the tubing, okay? Because now the tubing is narrower than 2 millimeters and you're making a reverse horn and you're cutting off the highs. So clinicians always need to be taught how to change the tubing in an ear mold, and you'll learn that, okay? Back to share screen. Heavy walled tubing you can sometimes order, gives greater durability, but tends to have a smaller internal diameter. May reduce feedback, but may reduce the highs too much. Sometimes anti-perspiration tubing can be bought, but whatever, don't worry, that's all number 13 tubing from here to here. Today, we mostly are looking at, especially for mild to moderate loss, thin tube BTE. Tubing is about 0.8 to 0.9 millimeters in diameter. And let's look at our PowerPoint slides. And remember here, never confuse thin tube open fit BTEs with receiver in canal hearing aids. They look similar, but as I've shown you before, they're different animals. So as we go here, this is the large BTE, number 13 tubing, more for severe hearing loss. What kind of ear mold is shown here? A skeleton ear mold. There's the vent. Here's the mic. The speaker would be right in here. This is the ear hook. There's the number 13 tubing going into the skeleton, lucite skeleton ear mold. Battery compartment, off telephone mic switch. They don't want to use off and on because O's, both off and on, both start with O's. So M is microphone, that means on. O means off. T means telephone mode. You'll learn more about that. Volume control. So those are the pieces and parts. And if you opened up the back door of the hearing aid like I just did earlier, you'll see the controls. That's in older hearing aids. Today, they're all digital. But the high-power hearing aid may look quite similar, but you're no longer physically adjusting this stuff that I'm circling here with a screwdriver. You're adjusting it by computer. Here's the basic parts again of a large BTE, the microphone, the hearing aid, the tubing, the ear mold. Again, that's a lucite skeleton ear mold with a vent in it, right here. Location of filters, often in the ear hook, not commonly used anymore. Number 13 tubing comes like this. It's like it's cut or sliced at one end so you can stick it into the ear mold easily and thread it. And then you'll grab that thin end here with the pliers and pull it through. There's the bend, and that bend allows the hearing aid to, there's the bend. Okay. Threading and tubing a new tube into an ear mold. This is a thin tube open fit BTE, just like I showed you. There's the dome. Okay. Thin tube open fit BTE. There's the picture again. Here's how it would look in the ear canal. There's that little wire thing. That's this thing here shown on the left. It's just meant to anchor it in place in the concha bowl. Thin tube effects tend to take away the high frequencies, so the thin tube hearing aid, see here's regular tubing, black, and then with the thin tube, okay, you're dampening the high, so the hearing aid has to deliberately make up those highs, and they do. Here's receiver in canal hearing aid. Looks a lot like the thin tube, except here a wire goes through the tube, linking the amplifier to the speaker, which is inside the dome. There's your dome, there's the speaker. So the receiver or speaker is here, whereas in the thin tube BTE, it's inside here, just like it was in the regular BTE. The speaker is up here too. So I hope this little session has kind of given you an example of a thin tube BTE. I should say of a RIC, a resound. There's a wire going through. See the wire going into the receiver or speaker? This is a right ear one because it's red. If this was blue, it would be the left ear hearing aid. Okay, so I hope that this little session here has kind of given you a little bit of an introduction to the shape and form and styles of hearing aids and to the non-electronic acoustic modifications of hearing aids. I can end this Zoom session now, and here's hoping that next week, a week from today, we can do a bit of a review of the entire course. All right, I'll sign off here and stop recording now.